Hey there, welcome. Today, we're basically becoming data detectives. We've got this set of messy, real-world measurements, and we're going to use them to hunt down a universal secret, a number that's been hiding in plain sight this whole time.
So our whole investigation kicks off with a really simple question. Just think about any circle you can imagine. A tiny coin, a massive car tire, the top of your coffee mug. Is it possible there's one single universal rule that connects all of them, no matter how big or small? Well, let's find out.
All right, so the hunt begins. What we're looking for is a pattern, some kind of connection between a circle's diameter, the distance straight across the middle, and its circumference, which is the total distance all the way around. Okay, these are our clues. And look, this isn't some perfect, clean data from a textbook. This is a list of real measurements taken by actual students, probably with things like string and a ruler. So you can totally expect some little wobbles, maybe a few slips, some rounding. In other words, you can expect some noise. This is what data from the real world actually looks like.
But here's the secret weapon, the key idea that gives us hope. In geometry, all circles are what we call similar. That just means they're all perfect, scaled up or scaled down versions of each other. And that implies something really profound. The ratio between a circle's circumference and its diameter should always be the same, no matter the size. So if you double the diameter, you've got to double the circumference. That strongly suggests there's a consistent straight line pattern just waiting for us in our data.
Now, just staring at a list of numbers is pretty tough, right? The best way to actually find a pattern is to see it. So let's plot all these measurements on a graph and see what happens.
And boom, just like that, a pattern practically jumps off the screen. Each of those black dots is one of the student's measurements. And even with all that real-world messiness we talked about, you can clearly see the points are arranging themselves in what looks like a straight line. The bigger the diameter along the bottom, the bigger the circumference up the side. It's a clear, positive trend.
Okay, so our eyes can see the trend, but to really analyze it, we need a proper mathematical tool. We need a way to draw the one single perfect line that best represents the path that these dots are taking.
And that tool is called linear regression. Its whole job is to look at all those scattered points and figure out the one unique straight line that slices through them so that the total distance from every single point to that line is as small as possible. You can think of it as a mathematical way of drawing the perfect line of average through the data. And here it is. That red line is our regression line. Notice how it doesn't try to hit every single point. That's not the goal. Instead, it carves a path right through the middle of that whole cloud of data, capturing the main relationship while pretty much ignoring the little measurement errors. This line is now our official model of the data.
So we have our line. But any line in math has an equation, a formula behind it. And that formula, well, that's where the secret we've been looking for is hiding.
This is the equation for our red line. It's our model. It's saying that you can estimate the circumference by taking the diameter, multiplying it by 3.147, and then subtracting a tiny little bit, negative 0.24. Now what's that about? Well, that little number is the intercept. In a perfect world, a circle with 0 diameter should have 0 circumference, so the line should go right through the starting point. This tiny number shows us there's probably a small, consistent error in the measurements. But you know what? It's so close to 0, which is actually a fantastic sign.
But the really crucial number here is the other one, the slope. That 3.147, that's the rate of change. It's telling us that for every single centimeter we add to a circle's diameter, our model predicts that the circumference is going to grow by about 3.147 centimeters. This number right here is the very heart of the relationship between these two measurements.
So does that number, 3.147, ring any bells? Let's put it side by side with the famous mathematical constant, pi. The value of pi is roughly 3.142. Our slope, which we got purely from those messy student measurements, is 3.147. That is incredibly close. We actually found pi. It was hiding in the data the entire time, just disguised as the slope of that line.
This is amazing. But, a good data detective always questions their assumptions. We picked a straight line model because we had a hunch about circles being similar. But what if we were wrong? What would happen if we tried to fit a different kind of model to our data, say a curve?
Well, this just shows why our first choice was absolutely the right one. On the left, you see our beautiful straight line model fitting the data like a glove. And on the right, that's what happens when you try to force a logarithmic curve onto it. You can just see how that curve completely misses the mark, especially for the bigger circles.
The visual proof is overwhelming. This relationship is definitely linear.
So, what's the big takeaway here? Let's just step back and wrap up what our investigation really found.
This final graph really says it all. The black dots, that's our real messy student data. And the solid line, that's the perfect theoretical formula for any circle. Circumference equals pi times diameter. Just look at how closely our real-world data points hug that perfect theoretical line. We used an imperfect, messy process to uncover a perfect, universal truth.
So, let's just recap the journey real quick. We started with just a jumbled table of noisy numbers. We put them on a graph to reveal a hidden, straight-line trend. Then we used the tool of linear regression to give that trend a mathematical definition. And when we did that, the slope of our line revealed itself to be a fantastic approximation of pi.
And that kind of leaves us with one last big thought. We just found one of the fundamental constants of the entire universe hiding in a handful of measurements of things like coffee cups and bottle caps. It really makes you wonder, doesn't it? What other incredible secrets are just waiting out there to be discovered, hiding in plain sight in the data that surrounds every single one of us every single day?